Since we're talking about image and printing fundamentals, and we spent a fair amount of time talking about the input end, that is whether we're creating and working with RGB or CMYK images and how we measure them with the info tool, I'd like to now switch to the output end and talk a little bit about what happens to our images when we actually output them on a printing device. Well, nearly all of our images, when we print them, we hit the print button and send them out to a printing device, they go through what's called a raster image processor. And what this raster image processor, commonly known as a RIP, does is it takes and converts your pixels in your Photoshop image into a pattern of spots and dots. And that's how your image is actually reconstructed on the printing device. And what I want to talk to you about is that there's a couple of different types of dots or spot patterns that can be used in processing your images. Here you see a real simple example of what happens when a very simple image like a piece of line art gets converted into small image spots. Here you see a very hard edge black and white like this, which when you enlarge it and you look at the pixels would be built up something like this, but when it goes to the printing process, that gets converted into a very straight line of connected spots. Well, the same kind of thing happens with a continuous tone image like a photograph, but instead of using tiny little individual spots, we use actually patterns of dots, and dots are constructed out of those tiny little spots. So if we have a continuous tone image, let's say we scan or a digital camera, we convert that original image or original scene into a pattern of pixels. 3 grayscale channels for an RGB image or 4 for a CMYK image. And then we edit those pixels to get the values that we want. Then we process them through a RIP, and we get patterns of dots. This is commonly and historically called a halftone dot pattern. What we see over here is the two kinds of dot patterns that we use to reconstruct images in our current technology. The first one on the left side is the conventional halftone dot. This is what is still used by many commercial printing presses and commercial printing companies. And here the conventional halftone dot, also known as an AM dot, and I'll come to that in just a minute, why we call it an AM dot. But let's first look at their characteristics. Notice that these dots are equally spaced. And this is contrasted with what we call an FM screen or an FM dot. Instead of a standard halftone dot pattern, you'll very often hear this referred to as a stochastic dot pattern. There's multiple names for these things, but what's important for you to understand is that these two different dot patterns are constructed and work in slightly different ways. Notice that the FM screen has much smaller patterns of dots, whereas the AM screen has larger patterns of dots. You also noticed that these AM or conventional halftone dots are equally spaced, whereas the FM dots appear to be, well, kind of randomly placed, which is why they're called stochastic. And in fact, that's true. AM halftone dots tend to be very evenly spaced, FM dots don't. AM halftone dots tend to be larger, whereas FM screen dots don't. And one of the fundamental differences as to how these work is that we create perceptions of grayscale values with conventional screens by changing the size of these halftone dots. Here you see a halftone dot that's taking up about 50% of the space here. That creates about a 50% grayscale value. But with an FM screen, instead of changing the size or the dimension of the halftone dot, the FM screen dot size remains the same, and we either pack them in closer together or spread them further apart. Hence, we use the names AM and FM screen, where AM stands for amplitude modulation, like on an AM radio. We're changing the amplitude or the size of the halftone dot. Whereas in FM, which is frequency modulation, we're changing the frequency or the spacing of the dot. This is most easily seen when we look at gradients. Here's where you can really see the difference between an AM and an FM, or a conventional halftone and a stochastic dot. As you go from light to dark, notice the halftone dot pattern here. The conventional halftone dot is getting larger and larger and larger, but the spacing remains the same. Whereas here, with the FM dot, you see that the dimensions or size of the FM dot is constant, but the spacing or frequency gets tighter and tighter and tighter. Why is it important to understand the difference between these two? Well, different output devices use different screening technologies. First of all, a conventional offset printing press typically uses AM screening. There are some conventional printing presses and conventional commercial printing companies that actually use FM screening. And it's a good thing to ask for, and I'll tell you why in just a minute. But understand that most conventional printing presses use this kind of a screening. Whereas most of your inkjet devices, your high-quality photographic type inkjet devices, will use an FM screening pattern. This is one of the reasons why you can get very high-quality, near continuous tone looks on an FM printing device, because you're working with such small dots. It more closely resembles what a continuous tone image looks like. Whereas with an AM dot, there's a definite pattern in there that the eye picks up. There's also another difference in terms of printing between an AM and an FM dot. With an AM dot, if you look carefully in this example, you can see not only do you see standard dot patterns, but if you look out, you can see kind of these squares of halftone dots. Anytime you print an image that already has a pattern in it, and you try to print it with a standard AM dot, you can get this repeating pattern. It's called a moire pattern. And it's one of the things you have to look out for when you're printing images that have patterns in them on a standard AM halftone dot press. Whereas you're printing that same image, such as a tweed coat, let's say, that has a very obvious herringbone pattern in it, when you print that on an FM device like an inkjet, then you're far less likely to get the moire pattern or the repetition of a pattern that is created between the AM dot and the actual pattern that's in the image. One final difference between these two, which we'll come to later in this course, is that AM and FM printing devices have different resolution requirements, so that it takes more pixels per inch to actually print an AM dot than it does a typical FM dot, which means that you can actually print larger images with the same amount of resolution on an FM device than you can with an AM device. So those are the two different types of screening technologies that we work with, AM and FM. And in your mind's eye, then, what you can think about and remember is you start with a continuous tone image, you scan that image, and let's say we start with a 50% grayscale area, and you create a 50% grayscale pixel. If your printing device is calibrated and set up properly, that 50% pixel becomes either a 50% halftone dot or a 50% spacing of FM dots when it goes to either a piece of film, which is very uncommon these days, or a plate, or directly onto the printing device, such as a digital press or an inkjet device. So the fundamental concept to kind of keep in the back of your mind is that regardless of what kind of printing device you're working with, nearly all of them will use some sort of a dot pattern to recreate your images. Some devices, like a standard commercial printing press, will use the standard halftone dot, which is known as an amplitude modulated dot, in which you're changing the size of the halftone dot in order to reproduce a specific tonal value. Whereas other devices, such as a lot of toner-based devices or inkjet devices, tend to favor using an FM or frequency modulated dot, in which the dot stays the same size, but you vary the spacing or the frequency in order to, again, reproduce your tonal value. Your goal in printing is to try to reproduce the same tonal value that's in your final image on the final output device.